So as I mentioned before, structured light systems are very widely used in the real world for many different applications. It's a very large industry. The design and the creation of these systems, a multi-billion-dollar industry, and they're used in many different domains. They're very sophisticated in terms of the lighting systems that they use, the image capture systems, the positioning systems, and so on. What I want to do here is just show you a couple of examples that represent what the state of the art is in terms of structured light systems. So here's the first one. This is a system that's been developed for 3D visual inspection by Omron Corporation. And typically these systems look very much like this. They are large systems because the part, for example, a printed circuit board, has to go into the system and has to be scanned very precisely, and the inspection has to be done in real time. And then by the time the part comes out the other end, you have a complete three-dimensional model of the part and decisions with respect to the quality also made. So you can see here that the part, there's a feeder on the right side, and so the printed circuit board is fed in. There's your structured light system with cameras and lighting, etc. And the PCB is being scanned in terms of tiles. You see that there is the phase shifting method being applied to these different tiles at a very fast pace. And when it's done, you have a complete three-dimensional model of the printed circuit board. So here you see one of the components, its shape, as well as a solder joint associated with it. Solder joints are extremely important because we want to know whether the connections are being made. And when defects are found, then the object or this part is then channeled through a different part of the assembly pipeline so that it can be further inspected. And if a part looks good, it just goes on to the next stage. So there's a very sophisticated systems in terms of the lighting, in terms of image capture, but also in terms of positioning. You need to be able to very accurately position these parts while you're scanning them. And then here is another example. It's not really a system, but rather a project. This is the Digital Michelangelo project, which was led by Mark Lavoie back in 2000 at Stanford. And it was a group of 22 people who went to Italy to scan some very well-known statues and various artifacts. They scanned these objects over a span of 30 nights, it says right here, using fairly sophisticated, highly calibrated structured light systems. So here you see structured light being applied to David's face, and you can get models that look like this, very precise models. This is what we'll call virtual David. If you look closer, you see the quality of data that you end up getting, even closer and even closer. And the depth in this case was calculated with an accuracy of 1/4 of a millimeter, very precise. Now you can imagine that using this model, you can create a virtual museum. You can also then use this model to, over time, repeat scans and figure out which parts of David are decaying, have damage, and so on and so forth. So that's for archival purposes. A similar project was led by Katsushi Ikeuchi, and this is called the Great Buddha Project. And so his team, again a large team, was able to create digital models of various monuments in Japan, Cambodia, and other places. So here is the Great Buddha in Nara, and here is the digital model of the Buddha. And these are very challenging projects that require many different structured light techniques, illumination techniques, but also in this particular case, you can imagine the size of the model itself is such that one can't simply scan these like you would small objects. You need sometimes to even use drones to go in and capture information. And then finally, we talked about the light stage technique that was developed by Paul Debevec and his team. And I want to show you another version of the light stage, which uses many different structured light techniques. So again, As we know, the light stage uses a very large array of LED light sources that can be controlled in terms of color, brightness, and duration. But this particular stage also includes an array of cameras, different types of cameras, color cameras, infrared cameras. It projects illumination patterns in the infrared domain so that you can get more detailed three-dimensional structure. And you're able to control the lighting, the camera system to capture enough information in a short duration of time so that you can actually get surface normal information, depth, the diffuse reflectance, as well as the specular reflectance. And once you have all of that information, you can then take whatever this object is that you're scanning and drop it into another environment and relight it. In this particular case, we're looking at what's called performance capture. So you see here that you have a person who's walking. These are the multiple views through the different cameras. There's structured light. And then here you can see the lighting being changed. It's being slowed down. You get surface normal information, depth information. There's your diffuse albedo, and there's your specular component. And now this person or his digital form can be dropped into some other environment. And if you know the lighting there, you can render it very accurately. Very ambitious project. Now, having gone through all of these different techniques, it's worth also taking a look at some of the unsolved problems in the context of structured light. So one of the challenges with structured light is when you're dealing with surfaces that are not really opaque. So when you have surfaces that reflect light at the surface itself, and light doesn't really enter too deeply into the surface, then the structure of the light patterns end up being preserved. They end up being sharp. But when you have something like skin, say for instance, I'm not sure if you're able to see this, but if you shine a point of light on skin, what happens is that the point appears actually bigger. And that's because light enters one point and actually re-emerges because of the translucency of skin, re-emerges at a neighboring point. So these are fairly challenging cases. That's also being shown right here. Because when you do structured light, remember that you're assuming that the point is being lit and not being by the light source and not being impacted by other points. So interreflections and subsurface scattering remains an unsolved problem, a challenging problem, a very interesting research direction. And then you have participating media. Let's assume that you were talking about scanning something in the presence of fog or underwater in murky water. And in these cases, when you throw out structured light, a light pattern, the pattern itself is going to decay rapidly as it travels through the participating media. And in addition to that, the medium itself begins to glow because of this light. And so these are very hard measurement problems, and structured light underwater, say for instance, has many interesting challenges. And here's another obvious one which we've discussed before, which is the scanning of mirror-like objects, very shiny objects. This continues to be an open problem because, as we know, a specular point, a mirror point, reflects light only such that the angle of incidence is equal to the angle of reflection. So you have to be in the right place, given a light source. You've got to be in the right place to capture a reflection. So that's another challenging problem. And then, of course, you have transparent objects that might bend light, that might just have light pass through. How do you recover the three-dimensional shape of a glass that is completely transparent? These are challenging problems that new methods are being proposed for. And finally, I want to mention very fine-scale recovery. So when you think about things like hair, one strand of hair can end up being substantially smaller than, or its projection onto the image can be much smaller than the size of a pixel. So you could have multiple strands of hair that are running through a single pixel in the image. And the question is, how do you get detailed reconstructions of hair so that when you then use them for relighting purposes or dropping them into various special effects, you want to make them look really realistic, and that requires you to estimate or recover the hair with high accuracy. That still remains a challenging problem.